to continue on computational heat and fluid flow. So the last thing that we saw yesterday, that was this method, that we have here, the TVD Runge-Kutta method by Gottlieb and Schuh. So, and we saw that this consists essentially of three Euler steps. The first is an Euler step, where we apply the explicit Euler method to solve our system of ODEs that we get from the finite volume discretization. And then we get the first stage value, U1. We use that here to evaluate the residual again with that new value. And then we have here some weighting of the old time level and the first stage. And then also the weighting that we have here in front of the delta t, the residual term. And we do the same thing in the next stage. In the third, we get first the two-stage value u2, and we evaluate again the residual with that value. We weight then this, what we get there, delta t times the residual with 2/3, that just happens to be this constant, and use also the old solution, un, and the solution at the second stage. And then we get the solution. So we need to do 3 stages. And the work is to do these residual evaluations. So we have 3 times the work of an explicit Euler method, but we get third order. But that's not the main point, as we shall see today. The main point with this method is we get a larger stability domain. So that is the main point. And we shall look now into the stability in more detail. So the equation 3 that we were discussing, that is this equation 7.4 in the lecture notes. So we want to discuss the stability of the TVD Runge-Kutta method. I call it RK3 because it's third order. That was the equation 3. By the way, the TVD, they changed the name later on. They call it strong stability preserving. Like for the explicit Euler method, this method has the same property that we get strong stability when we apply it, for example, to a scalar conservation law, as we discuss here. So stability for this method, when it is applied to our system of equations that we get from the finite volume discretization, with the right-hand side with the residual 2, that is now analyzed, that is what we shall start today, that is analyzed by the von Neumann stability analysis. However, we have a problem. The problem is the von Neumann stability analysis is only valid for problems with constant coefficients and for periodic boundary conditions. So we have neither of them. So what do we do? The first thing is to get the problem linear, we linearize it. And it has turned out that the analysis for the linearized problem is a prerequisite for the stability of the nonlinear problem. So, and usually it is enough, so that we are lucky there. So that means the first thing is we have to linearize our problem. So linearizing, and when we linearize, we get still a nonlinear problem. We get a nonlinear problem, but we need then to take this point that we get at the value that we get at a certain point, we call that localizing. You'll see that in a minute how that works. And we do then, in our case, we do that for the PDE in the first place, and then also for the numerical method. To show what this means is when we look at the inviscid Burgers equation, we have this nonlinear flux that we have to derive with respect to x in the equation. But we know if we have a smooth problem, then we can write this here as ux. In the general case, this would be the f prime of u, which in our case is u, times the ux for a general scalar conservation law. So this is just an example. So this is clearly nonlinear because u is unknown and ux is the unknown, the x derivative of the unknown. So that becomes, when we do the linearization, then we take that, and then we take this as a, and that now is the localization, that we take this as at some point x0 and say at some time tn times ux. So the u that we have here, let me write it a little bit better for those sitting in the rear. So we have u squared half x that is equal to the ux. And that is then approximated by the u of x0 tn times ux. So this u here is then taken at one point in space and time. So that is the idea. In this way we get a quasi-linear form, but here we get then a fully linear problem, and we call this here then a ux. So the a is then some, in our case, some velocity at some point at some time level tn. So that means in this case we assume then that the a is constant. So we replace the nonlinear problem by a linear problem. And we assume that we have periodic boundary conditions to be able to apply for Neumann stability in others. So assume periodic boundary conditions. So then we can go ahead with the Neumann analysis. And then we can do what we usually do. We can use a Fourier mode and test everything for just one Fourier bound. Of course, they are linearly independent for the different wave numbers, so we can do that. So then we insert a Fourier mode, and that is then the uk hat. And now we take that continuous. That's the catch here. Usually we took it at the time level n, now we take it at some time t. So then we have the full time dependence of the amplitude of the Fourier mode, and then it has then a trigonometric form in space, which we can then represent by the exponential e to the imaginary unit I, k wave number, xj, our grid point. We insert that into the finite volume method, which we consider as, to be able to use the theory, considered as a finite difference method. So they are the same when we are in the interior for our problems. And we insert that for the uj. So that means the uj in the discretization is replaced by this Fourier mode. And then the result of that is that we get something that is called the Fourier symbol. So the Fourier symbol, and that is then something that depends on the wave number times the grid space in delta x. So that is a little bit abstract, so we get an example to see what it means. And the example is that we look now for the linearized problem. That is, we have here then a convection term with a constant a, and we assume even that we have a viscous term with a constant viscosity coefficient mu. So that is an example of a convection diffusion equation. Here we have the convection part, here we have the diffusion part. We started the lecture with the course with considering just diffusion. We looked at the temperature, so U was the temperature in that case. Then we looked just for the convection, And then now we are looking for nonlinear problems, but here we do a linearization. But now we combine them. That is also what we do with the Burgers equation. So we want to discretize this convection diffusion equation with the central finite volume method. So we discretize that, discretized by the central finite volume method. If we do that, and you have been doing that usually here for the diffusion term, usually not for the convection term, but if we do it here now for the also for the convection term, we get the following. So that is equation 5. We get the time derivative of our approximation to the cell average in the cell J is equal to, and now we divide it by delta x. We assume we have an equidistant grid. So we have our convection velocity, and then we have a central discretization. So then we get this in the end, uj plus 1 minus uj minus 1. So that is what we have not used so far, for good reason, because we just would stop here for the linear affection equation, and we would use explicit Euler. We have, some of you have looked at that, that is unstable. But now we check it. But we check it even with the diffusion term. And the diffusion term here, that is then u divided by delta x squared, and then we have the usual discretization of the second derivative if we would do finite differences, but we arrive at the same result with the finite volume method. Like that. Oops. So that is then the discretization. Just the finite volume discretization giving us the same result as we would get with the corresponding central finite difference method. Now we do what we said before. We replace uj by the Fourier mode, that is uk hat, and we remember this is a function of t, that is e to the I kxj. So we do this replacement. And then we shall see that we can, after we have done it, inserted it, we can factorize this term, and we end up, that you might take as a little exercise, to do that, we end up with the following. We get the time derivative of the amplitude, and on the right-hand side, we get minus a divided by delta x, and from the central discretization, we use Euler's formula here. So we get in here now the imaginary unit, and you get in the sine of k delta x. So that is coming from the discretization of this part here, and we factorize the amplitude. So that is then coming from this, and this term here, that will lead to a similar term as we did for the Fourier analysis for the heat equation. So, and then we'll get here minus, we can write it in this form, where we have used a trigonometric identity for 1 minus cosine of k delta x, and we get here then the sine squared of k delta x half. So then the big bracket, and then we have to factorize the u hat k, the amplitude. So we get this form. And all we have done here, we have inserted this here. We have used that xj plus 1 is xj plus delta x. xj minus 1 xj minus delta x, and so factorize, so that we in the end can factorize this whole term, use Euler's formula, use this geometric identity, then we get that. And this term that is here in front of the uk hat, that is called the Fourier symbol. So that is our lambda of k delta x. So that is called the Fourier symbol. So in a sense, it is the Fourier transform of our difference operator. And we get a very simple equation that we can solve immediately. We get something that resembles, that is actually Dahlquist's test equation. We have a linear equation. This is some constant, it is imaginary, it doesn't matter. We have a time derivative is equal to a constant, this Fourier symbol times the unknown. So we know the solution. The solution is the initial condition on that times e to the lambda t. So then we know that. So, and now we do the analysis by doing the analysis for the time discretization methods that have this form. And that is then we essentially use the result from stability theory of ODE methods. So for a time discretization method, to be stable, then the requirement is then that this lambda, it depends in our case on the wave number and delta x, times the time step delta t. That must be in the stability domain of the ODE method. That is then the condition to get stability. That must be in the stability domain of the ODE method that we use to solve our problem in time. So, and then we have to know what is the stability domain. So here we have then the example of the symbol, Fourier symbol, and now we proceed then. Now we look then what is the stability domain. So the stability domain of an ODE method is defined by following. That is a set, we call it S. It's then specific to one ODE method. For example, explicit Euler method or TBD-Runge-Kutta method, whatever we like. It is the set of all complex numbers for which the stability function, we define that shortly, I give it a curly r, stability function of z is smaller equal than 1. So this, and the stability function, that is then what we get when we solve our ODE problem, not itself, but for the Dahlquist test equation. Because that is what we have here. We have here for, when we do this Fourier analysis, we get Dahlquist test equation where the lambda is the Fourier symbol. Yes?
Can you explain number 7 again?
I think it is the set of all complex numbers for which this stability function in absolute value is small equal 1. So I have to explain that first.
Okay.
And that's what we do. And then we see examples, then I think it gets clear. Just wait a little bit. Yeah. So where the stability function, and that is then a function actually of lambda delta t, is the stability function, that is the name. And the stability function, that is the solution of Dahlquist test equation. So that is what you might know from numerical analysis. The Dahlquist test equation, and that is after one time step. So we just do one time step with our method on this Dahlquist test equation. So after one time step. So that is the following. The Dahlquist test equation is this here, which is y prime is lambda y. Y, you can think of a scalar, an unknown function, y of t, and we have the initial condition, y of 0 is y0 is equal to 1. So that is the Dahlquist test equation. So it's extremely simple. It's the basis for this analysis of OD methods. And what we do when we work with that, we assume then that the z that we are working with, the z, is corresponding to the lambda delta t. So the lambda is the lambda that we have here, and the lambda that is complex and it is constant. Lambda is constant. And in our case, what we are discussing, the lambda is the Fourier symbol that we get from the discretization of our convection diffusion equation. So we had it seen before for our example. Now we want to see examples of this, and then also to see examples of the stability function, and then example, when we know that, then we can also check what is then the stability domain. So we start, of course, with the simplest example possible. That is example 1, and that is the explicit Euler method. So that is, then we look for the explicit Euler method. So we want to determine first the stability function for that, and then we want to see what is the stability domain for that. So what do? We do one step with the explicit Euler method to solve this equation. One time step. So we say then y1, that is the solution at the time level 1, is equal to the solution at the time level 0, plus, what is the rule for the explicit Euler method? We take then plus delta t times this at the old time level. So then we take the delta t times the right-hand side, which is lambda, and the old time level is 0. So we see we can factorize then the y0, that is the solution at the time level 0. And that is then equal to 1 plus, now I write it as lambda delta t, times the y0. And the y0, well, here I use this, I could have also written the index here as the initial condition. So this is 1 in our case. So that means, and this we call z. So that means what we get here is then we get simply 1 plus z. So then from that we can then say that the stability function for the explicit Euler method is 1 plus z. So the solution that we get after one time step is y1, that is our stability function, and what we get we express with z. So this is the result. That is the stability function for the explicit Euler method. And if we want to know then the stability domain, we look for all values such that the absolute value of 1 plus z is smaller or equal than 1. So that is the stability domain. Let's see for that. Well, can we understand what this is? Let's see if we... So then we look into the real part of lambda delta t, and we look in the imaginary part of lambda delta t. So that is essentially the z. And then we can check that is assumed z is 0. So then we are here. For 0, 1. So we have to check then the stability domain is then for the explicit Euler method. Explicit Euler. That is then the set of all complex numbers for which the absolute value of 1 plus z is smaller or equal than 1. So then we have already now found out the 1 does it. So that is inside. If z is real, then we can go up to -2. For -2, 1 minus 2 is -1, absolute value is 1. So anything on the real axis, if we go here until -2, also note that we have -1 here, we have the origin, that will be inside the domain. And what else? Well, we can think of when we would write the z as -1 plus what we call it r e to the I5, for example. So that would be any complex number that lies on a circle with a radius r. So my claim is now, if we choose r equal 1, we get a circle with a radius 1. So this is the radius 1. And I claim that this will do the job. You see, if we plug this z here, which is all points here for, in that case, if I take that away, then it is r equal 1. Then we have all points, if we vary phi from 0 to 2 pi, we have all points on the circle. And if we plug that in here, then we get 1 minus 1 is 0 plus e to the I phi. So then, in our case, we get then that the r of z is, in our case, of this z, is then the simply e to the I phi. And that says is smaller equal than 1, and that is true. That is cosine squared plus sine squared, which is 1. So, in our case, we find out that everything that lies in this circle around -1 with radius 1 fulfills this condition, that the absolute value of the stability function is smaller equal 1. So if we have some lambda and we choose delta t such that we are inside this domain, then our method is stable. That's the conclusion. In our case, we get the lambda from the Fourier symbol, so we have that, and then we check lambda delta t, is it inside, stable, is it outside, unstable. So that is then the idea. So that was example 1. Now we look for example 2. We come back to the Rada-Kata method.
What about 0? Is included or excluded?
We have already included.
Ah, okay.
So that was the first thing that we discussed. If you have 0, we have 1. 1 is smaller equal 1.
Yeah, no, just because I think I have a different convention with the dots. So if it's empty, I think it's excluded. When it's full, yeah, okay, it's fine.
Well, for me this is mathematically clear. It is
okay.
absolute value of 1 plus z smaller equal 1. Equal is included.
Yeah.
So that is mathematically, I think, no discussion.
That was just about the drawing, but that's fine.
We have an empty circle at the origin. For him, that's not included.
It was just pointing out that that's the origin.
Okay.
It was not meant anything. It was just
Okay.
indicating it's the origin.
Okay.
It is not. It is 0 is included.
Okay.
Point. So example 2. That is the TBD Runge-Kutta method. TBD RK3 or third order Runge-Kutta method. So then we do the same thing. So then we insert, we apply the method then for solving this equation. So we don't have u, we have y, and our r of u is lambda y. So extremely simple, we plug that in. That is a matter of 3 stages, and the result is that we get y. I don't do this, you can do that yourself. That is by inserting lambda y for r of u in 3. That is in equation 3. Then we get this equation, we get this here. So that's the y1. And then we get, in fact, the following. We get 1 plus, and we get lambda delta t. We get lambda delta t squared half. And we get lambda delta t to the power 3 divided by 6 times the y0, which is 1. And this here is then our function r of lambda t. So this is, we write this here, that is the stability function of lambda delta t, which we call then the z. So from that we get then the r of z, and that is then the following. So that is then the stability function for the TBD Runge-Kutta method. That is 1 plus z squared half plus z to the power 3 divided by 6. And then our stability domain is then the stability domain of the TBD RK3 is the set of all complex numbers for which this in absolute value, that is 1 plus z squared half plus z to the power 3 divided by 6 is smaller or equal than 1. By the way, you see here that we are approximating the exponential e to the power z. Here up to the third order, so it's fourth order accurately. So, but this is then our stability function, and then we have to find out where is this true. And that can be done. It is can derive that, and you'll find that in textbooks, and we have here at NTNU very good experts on that. There's a textbook by Haira Nørset-Vanner, and Sivert Nørset is from NTNU. So there you find all the details. Let's see, I just want to show you the result that we get from that. So we can, of course, compute then this the stability domain, the boundary, and let's see, let's do that. So RK domain. Here we are. So here we have the stability domains for actually 3 methods. The one that we have discussed, that is example 1, that is the blue circle, that is the stability domain for the explicit Euler method, and the one that we have not yet discussed, but what we can see here, that's the red one. The red one is the stability domain for the TVD-Runge-Kutta method. And the green one that we have not discussed is for Heun's method. That is a second-order TVD method. But you see here some problem both with the explicit Euler method and with the Heun's method. Because if you remember, our Fourier symbol, lambda, was containing an imaginary part, and that was coming from the central discretization. If we would not have any viscosity, our Fourier symbol would be completely imaginary. So then our lambda t, delta t would lie on this imaginary axis. That is the imaginary axis here. And on the imaginary axis we have only one point that lies inside the stability domain, both for explicit Euler, the red circle, and this ellipse shape looking like stability domain of Heun's method, that is 0, the origin. And that is uninteresting. That would correspond to, say, either as convection speed 0 or delta t 0. That doesn't make sense. So for any reasonable value of the Courant number, this method will be unstable. Both for the explicit Euler, we have proved that in an exercise, and also for Heun's method. But TVD-Runge-Kutta is, there we have it inside the stability domain. So we can go up to this point. It's about 1.7 on the imaginary axis, and here down it is minus 1.7 about. So there we get stability, even with the central discretization. So that's the big advantage of this TVD-Runge-Kutta method, and also, by the way, of the classical Runge-Kutta method, that it contains part of the imaginary axis. So therefore, this has a large stability domain, and that is very useful for us. So then we have to discuss that now to see the advantages then with this method compared to Heun's method, which is second order, or explicit Runge-Kutta method, which the explicit Euler method, which is only first order. So that is the main reason why this method is useful, and of course because it preserves the TVD property in time. We have a TVD method for the explicit Euler method, and it will also be TVD when we use this third order method. So then we look at these stability domains. Then we can do that. We started already with the explicit Euler method. We have the real part of lambda delta t, and we have the imaginary part of lambda delta t. Let's see if we do it for, we have here this one. This is again the origin. 1, 2, 3. Minus 1, minus 2, minus 3, and on the left we go, let's see if we could do it on scale, it would be something like here, minus 1, minus 2, minus 3 roughly. So then we have a circle, a circle here. Well, get it right here. Oh, it should be a circle. And that would be then for, that would be then the 2 here. That would be then for the explicit Euler method. And the Heun's method is a little bit larger. I think we get up to 1.7 roughly here. So let's see if we can do that in different colors. So maybe something like that. So let us indicate what we do here. So the that was then the explicit Euler method. Stability domain is the boundary of the stability domain of the explicit Euler method. That would be Hoyne's method. Second order Runner-Kutta method. And then let's see if you can see that. The TBD Runner-Kutta method, I have to find out first where I have to cross here. Let's see. Something like roughly like that. So well, it doesn't look very nice. It should be something like that. I think I didn't get it here so nicely. So it should be symmetric. And here it should end up roughly a little bit around minus 2.5 at this point here. And the point that we hit here is, let's see, it is actually 1.732. And here we hit minus 1.732. These points are actually important. So that would be then for the TBD Runner-Kutta method. Oops. RK3. And the method that you probably have learned in the beginning when you did ODE methods, numerical analysis, that was the classical Runner-Kutta method. Then we are here at, that is 2 square root of 2 on the imaginary axis, and we are here at minus 2 square root of 2, about 2.8, and we are here also at minus 2 square root of 2. So then that looks like, let's see. It should look like a kidney, but mine doesn't look very much like it. It should be something like that. So it should be some kidney shape. You have it in the lecture notes. There you have it better. So that would be then, the red would be then for the classical fourth order Runner-Kutta method. So the advantage there is you have here a larger stability domain of the imaginary axis. You go not just to 1.732, but you go to 2 square root of 2. And on the real axis, you go a little bit further than minus 2.5, you go about 2.8. It's not very much, but the main advantage is it is fourth order. So here you have first, second, third, fourth order. So these are the stability domains. Okay. So the important fact that we have here is that we have the TBD RK3. The stability domain RK3. So it is the stability domain of the RK, the TBD Runner-Kutta third order method, contains part of the imaginary axis, which neither explicit Euler nor Hoyne's method do. And in our case, that is the interval minus 1.732 to 1.732. So it is this interval here. That is from the green curve. So that is inside the stability domain. So therefore we can get stability, as I said, for a central discretization without viscosity. So for the inviscid, for the linear affection equation, we can get stability with a central discretization. Okay, but we stop here and finish up then after the break.